Episode 19. The title of the radio enabled learning course is Energy Physics, Unit 5, Solar Energy. In this episode 19, we will discuss about solar photovoltaic, that means solar cells. The direct conversion of solar energy into electrical energy by means of photovoltaic effect, that is the conversion of light into electricity. The photovoltaic effect is defined as generation of an electromotive force as results of absorption of ionizing radiation. Energy conversion device which are used to convert sunlight to electricity by the use of the photovoltaic effect are called solar cells. A single converter cell is called solar cell or more generally photovoltaic cell, and combination of such cells designed to increase the electric power output is called solar module or solar array. The photovoltaic cells are made of semiconductors that generate electricity when they absorb light. As photons are received, free electrical charges are generated that can be collected on a contact applied the surfaces of the semiconductors. Because solar cells are not heat engines and therefore do not need to operate high temperatures, they are adapted to the weak energy flux of solar radiation, operating at room temperature. These devices have theoretically efficiency of the order of 25%. Actual operating efficiencies are less than half of this value and decrease fairly rapidly with increasing temperature. The best known application photovoltaic cell for electrical power generation has been in spacecraft, for which the silicon solar cell is the most highly developed. The silicon cell consists of single crystal of silicon into which a doping material is diffused to form semiconductor. Since the early days of solar cell development, many improvements have been made in the crystal growing and doping, electrical contact and cell assembly and production of methods. Large number of cells have been manufactured with areas 2 into 2 centimeter, efficiency approaching 10 per centimeter, and operating at 20 degree or 28 degree Celsius. The efficiency is the power developing per unit area of array divided by the solar energy flux in the free space, that means 1.353 kilowatt per meter square. For terrestrial application, silicon solar cells have shown operating efficiency about 12 to 15%. Though silicon is one of the Earth's most abundant material, it is expensive to extract from sand, whereas it is occur mostly in the form of SiO2. And refine the purity requirements for solar cell. The greater barrier to solar cell application lies in the cost of the cells themselves. Reducing the cost of silicon cells is difficult because of the cost of making single crystal. One very promising method is being developed to produce continuous thin ribbon of single crystal silicon to reduce fabrication costs. Cells made from the ribbon have a so far shown efficiency of around 8%. Several other kinds of photo cells are in the laboratory stage of development. Cadmium sulfide and CDS or Cu2s cells are other possibilities. So far, efficiency have been in the range of 3 to 8%, and these cells have been less durable than silicon cells owing to degradation with exposure to oxygen, water vapor and sunlight, especially at elevated temperature. The active part of the cadmium sulfate cells is thin polycrystalline layer of CDS, about 10 micrometer thick, on which a layer of Cu2S compound, perhaps 0.1 micrometer thick, is grown. These cells can be made by deposition on long sheet of substrate, a process that might be adaptable to expansive mass production. Photovoltaic cells could be applicable to either small or large power plant, since they function well on a small scale and may be adaptable to local energy generation on building rooftops. The cost of the energy storage and power conditioning equipment might, however, make generation in large station the most economical method. Solar cells have also been used to operate irrigation pumps, navigational signals, highway emergency call system, railroad crossing warning, automatic metallurgical station, etc. in location where access to utility power lines is difficult. A PV photovoltaic system consists of solar cell array, load leveler, storage system, tracking system. In actual usage, the solar cells are interconnected in certain series parallel combination to form modulars. These modulars are hermetically sealed for protection against corrosion, moisture, pollution and weathering. A combination of suitable molecules constitutes an array. 1 square meter of fixed array kept facing south yields nearly 0.5 kWh of electrical energy on a normal sunny day. If the orientation of the array is adjusted to face the sun rays at any time, the output can increase by 30%. Solar photovoltaic system can be produce an output only if the sunlight is present. If it is required to be used during non-sunshine hour, a suitable system of storage batteries will be required. Solar cell principles. The photovoltaic effect can be observed in nature in a variety of material, but the material that have shown the best performance in sunlight are the semiconductors are stated above. When photons from the sun are absorbed in a semiconductor, they create free electrons with higher energy than the electron which provide the bonding in the base crystal. Once these electrons are created, there must be an electric field induce this higher energy electron to flow out of the semiconductor to do useful work. The electrical field in the most solar cells is provided by a junction of material which have different electrical properties. To obtain a useful power output from photon interaction in a semiconductor, 3 processes are required. First one is the photon have to be absorbed in the active part of the material and result in electrons being excited to a higher energy potential. The second one is the electron hole charge carrier created by the absorption must be physically separated and moved to the edge of the cell. The third one is The charge carrier must be removed from the cell and delivered to a useful load before they lose their extra potential. For completing the above process, a solar cell consists of semiconductor which electron-hole pairs are created by absorption of incident solar radiation, region containing a drift field for charge separation, and charge collecting front and back electrodes. The photovoltaic effect can be described easily for p-n junction in semiconductor. In an intrinsic semiconductor such as silicon, each one of the 4 valence electrons of the material atom is tied in a chemical bond, and there are no free electrons at absolute zero. If a piece of such a material is doped on one side by 5 valence electron material such as arsenic or phosphorus, there will be an excess electron in that side, becomes an n-type semiconductor. The excess electron will be practically free to move in the semiconductor lattice. When the other side of the same piece is doped by 3 valence electron material such as boron, there will be deficiency of electron leading to a p-type semiconductor. This deficiency is expressed in terms of excess of holes free to move in the lattice. Such a piece of semiconductor with one side of the p-type and other side of the n-type is called p-n junction. In this junction, after the photon are absorbed, the free electron of the n side will turn to flow to the p side, and the holes of the p will turn to flow to the n region to compensate for their respective deficiencies. This defection will create an electric field EF from the n region to the p region. This field increases until it reaches equilibrium for VE, the sum of the diffusion potentials for holes and electrons. If electrical contacts are made with the two semiconductor material and contacts are connected through an external electrical conductor, the free electron will flow from the n-type material through the conductor to the p-type material. Here the free electron will enter the holes and become bond electron. Thus both free electron and holes will be removed. The flow of electron through the external conductor constitutes an electrical current which will continue as long as more free electron and holes are being formed by the solar radiation. This is the basis of photovoltaic conversion, that is the conversion of solar energy into electrical energy. The combination of n-type p-type semiconductors thus constitutes a photovoltaics, that means PV cells or solar cells. All such cells generate direct current which can be converted into alternating current if desired. The most normal configuration for a solar cell to make p-n junction semiconductor, the junction of p-type and n-type material provides inherent electric field which separates the charge created by the absorption of sunlight. This p-n junction is usually obtained by putting a p-type base material in a diffusion furnace containing a gaseous n-type dopant such as phosphorus and allowing the n-dopant to diffuse into the surface about 0.2 micrometer. The junction is thus formed slightly below the planar surface of the cell, and the light perpendicular to the junction, the positive and negative charges created by the absorption of photon are thus encouraged to drift to the front and back of the solar cell. The back is completely covered by metallic contact to remove the charges to the electrical load. The collection of charges from the front of the cell is aided by a fine grid of narrow metallic fingers. The surface coverage of the conducting collectors is typically about 5% in order to allow as much light as possible to reach active junction area. If the junction is in thermodynamic equilibrium, then the Fermi energy must be uniform throughout. Since the Fermi level is near the top of the gap of an n-dope material and near the bottom of the p-dope side, an electric field must exist at the junction providing the charge separation function of the cell. Important characteristics of Fermi level is in the thermodynamic equilibrium, it is always continuous across the contact between the two materials. Each of the individual solar cells will produce power at about 0.5 volt with the current direct proportional to the cell's area. The individual cells are connected in series or parallel combination to meet the voltage power reliability requirements of the particular application. Space cells are converted with transparent cover slips to absorb the high energy particles in space that could cause damage in the cell, result in a degradation of output. For terrestrial application, the solar cell panels have to be encapsulated to protect them from atmospheric degradation due to oxidation of the metal contacts, which would cause peeling, and open circuits material such as glass, silicon, etc. are used to provide a clean weather fight front covering for the panel. Modern solar cells make use of semiconductor material usually based on single crystal silicon. When doped with phosphorus, arsenic and antimony, the silicon becomes an N-type semiconductor as stated earlier. And when doped with boron, aluminum, indium or gallium, it forms a P-type semiconductor. If P-type semiconductor is brought into intimate contact with one of the N-type, they form NP or PN junction. If the semiconductor material are derived from the same element or compound such as silicon, the system is referred to as homojunction. It is also possible for PN and NP junction to be formed from two different semiconductor material such as cadmium sulfate CDS and cuprous sulfate Cu2S. This is known as heterojunction. The general behavior at the junction as outlined above is the same regardless of the type. The Schottky junction consisting of a semiconductor and metal, this junction is formed by depositing a thin layer of metallic conductor, example platinum, onto a P or N-type semiconductor. Schottky junction photovoltaic cell made with the so-called amorphous silicon are more efficient than homojunction PN cells of the same material. Cost, if it is also less. The metal insulator semiconductor MIS solar cell is similar to the Schottky type except the very thin layer, about 0.1 to 0.3 micrometer of the insulator is deposited between the semiconductors and the metallic conductor. A conversion efficiency or more than 17% has been reported for an MIS solar cell made with an single crystal silicon. Conversion efficiency and power output. A solar cell usually uses a PN junction. Its physical configuration is shown. Current and voltage relationship is denoted as Ji is equal to J0 exponential of VE divided by KT minus 1. J0 is saturation current, also called dark current, and is obtained when a large negative voltage is applied across the diode. Capital V is the voltage across junction. Small e is the electronic charge. K is Boltzmann constant. T is absolute temperature. When light impinges on the junction, electron-hole pairs are created at a constant rate, providing an electrical current flow across the junction. The net current is thus the difference between the normal diode current and light generated current. Simplified equivalent circuit for the cell also constructed. The internal series resistance Rs is mostly due to the high sheet resistance of the diffused layer, which is in series with the junction. The light generation current acts as a constant current source, supplying the current to either the junction or useful load depending on the junction characteristics and the value of the external resistance. The net J current is given by J is equal to JL minus JI is also equal to JL minus J0 into exponential of VE divided by KT minus 1. The internal voltage drop in a cell can usually be minimized. A basic photovoltaic system for power generation. The first one is solar array, second one is blacking diode, third one is battery storage, fourth one is inverter or converter. The final important point is appropriate switches and circuit breakers. Thank you.